Alright, let's dive deep into the wild, weird, and mind-bending world of quantum mechanics. Now, before you roll your eyes and think this is just some boring lecture about particles and equations, let me assure you quantum mechanics is anything but ordinary. We're talking about a world where particles exist in two places at once, where light can be both a wave and a particle, and where observing something can change its state entirely. Sounds like the plot of an avant-garde sci-fi movie, right? Well, spoiler alert. It's actually how the universe works at the tiniest scales. Imagine stepping into a dimension where the rules of physics are completely different from what you know. In this dimension, atoms and particles don't behave in predictable ways. Instead, they're quirky, unpredictable, and downright weird. It's like the universe's secret party, and you're just a curious observer, trying to figure out who's who, while being blown away by the chaos. So let's start by understanding the first, most basic and most confusing concept in quantum mechanics: superposition. Imagine you're at a party, and you can't decide between pizza or pasta. So, in true quantum style, you just eat both at the same time, no need to choose. That's superposition in action. In the quantum world, a particle can exist in multiple states simultaneously. It's like being at two places at once, or if you prefer, eating both pizza and pasta simultaneously. Sounds great, right? Well, it's possible for particles, not just food. Here's the famous thought experiment: Schrödinger's cat. Don't worry, no actual cats are harmed in this experiment. Imagine you've got a cat in a box, and inside the box, there's a device that can release poison based on whether a radioactive atom decays. Now, because of quantum mechanics, the radioactive atom is in a superposition state. It's both decayed and not decayed until you look at it. Therefore, until you open the box and observe it, the cat is both alive and dead at the same time. But as soon as you open the box, the cat's fate is sealed. It's like deciding whether you want to be both a rock star and a scientist at the same time, until you check your calendar and have to pick one job for the day. This idea is so strange that even Einstein, the guy who gave us the theory of relativity, hated it. He didn't like the idea that particles could exist in multiple states simultaneously. He famously called this spooky action at a distance. And trust me, he wasn't talking about how creepy your aunt's email chain is. Now, let's talk about something even spookier: quantum entanglement. If you thought superposition was wild, wait until you hear about this. Imagine you've got two particles that are so closely connected that when you change something about one, the other instantly reacts, no matter how far apart they are. It's as if you and your best friend can read each other's minds across the universe, even though you're miles away from each other. Instantly. This means that when you observe one of these entangled particles, say, you measure its spin, position, or momentum, the other particle will automatically know and adjust accordingly, no matter if it's sitting in your room or on the other side of the galaxy. Einstein hated this too, calling it spooky action at a distance, because it seemed like it was breaking the rule that information can't travel faster than the speed of light. Imagine you're in a conversation with your friend, but instead of texting, you both just know what the other person is thinking, no matter how far away you are. This kind of instantaneous connection is at the heart of quantum entanglement, and it has been demonstrated in experiments, proving that particles really do act in this mysterious telepathic way. So next time you wonder how people always seem to text you exactly when you're thinking about them, just remember, maybe they've been quantum entangled. Now, let's take a look at Heisenberg's uncertainty principle, one of the more frustrating but crucial aspects of quantum mechanics. It's like trying to solve a mystery where you can only know part of the story at a time. Imagine you're a detective trying to solve a crime. You can either figure out where the thief is, or you can know how fast the thief is running, but you can't know both details at once. Why? Because in quantum mechanics, particles just refuse to behave like your standard objects. They're always a bit fuzzy. You can measure their position, but you'll lose information about their momentum. If you measure one property more precisely, the other gets more uncertain. It's like playing a game of hide and seek, where the person hiding always moves whenever you're not looking at them. This isn't because your eyes are bad or you're a lousy detective. It's just how the universe operates at the quantum level. The particles have no definite position or speed until you measure them. And once you do, you mess with their true state. It's like you and your friend being in two places at once. And as soon as someone looks, it's like the universe says, you can't have your cake and eat it too. Pick one. Now, let's dive into the concept of wave-particle duality, which is basically quantum mechanics saying, why not both? It's like light, electrons, and other particles can't decide if they want to act like waves or particles, so they do both. When light behaves as a wave, it does things like creating interference patterns. Imagine ripples in a pond when you drop a stone. But when you look really closely, light behaves like particles, which we call photons. It's like your best friend who is either super chill and artsy one day, and then suddenly becomes an incredibly focused, professional athlete the next. You can't quite pin them down. Here's the mind-bender, double-slit experiment. When scientists fired particles at two slits in a wall, you'd expect to see two bands on the other side, just like if you were throwing marbles through two holes. But instead, what they saw was an interference pattern, just like when you throw waves through two slits in a pond. How could this happen if particles were supposed to be solid objects? Turns out, when the particles aren't being observed, they behave like waves creating patterns of interference. But once you measure or observe them, they act like solid particles. So, are they waves? Are they particles? Quantum mechanics says, why choose? And just when you thought it couldn't get any crazier, enter quantum tunneling. This is where things defy the laws of classical physics. Imagine trying to push a ball through a wall. In normal life, you'd never get that ball to go through, right? It would just bounce back. But in the quantum world, particles can actually tunnel through barriers. It's like that scene in every superhero movie where a villain escapes by slipping through the walls only this time. It's not magic. It's quantum mechanics. Quantum tunneling is how nuclear fusion works in stars. Particles that normally don't have enough energy to get past a barrier, like the positively charged. Protons in the sun can tunnel through the barrier and fuse together to create energy. It's as if particles are like cheeky burglars who find a secret passage under a locked door. Finally, let's talk about quantum computing, which takes advantage of all this quantum weirdness. Traditional computers use bits that can be either 0 or 1, but quantum computers use qubits, which can be both 0 and 1 at the same time, thanks to superposition. This gives quantum computers an insane advantage in processing power. Imagine having a supercomputer that doesn't just think like a person trying to solve a math problem, but a person who can think about every possible solution simultaneously. The possibilities are mind-blowing. Quantum computers could potentially revolutionize everything from cryptography, breaking codes, to medicine, simulating molecular interactions, to predicting future events. While we don't have fully functional quantum computers yet, scientists are working on them, and it's like watching the future unfold in front of our eyes. So, quantum mechanics might seem strange, confusing, and totally mind-boggling at first, but it's also the foundation of everything from the electronics in your phone to the lasers in your grocery store scanner. It explains why the universe behaves in such strange ways at the smallest scales. And as we continue to unravel its mysteries, it might just unlock the secrets